In this video, we're going to be talking about how to find the probability of compound events. Now, compound events are events that consist of two or more simple events. So up until this point, we've only talked about simple events. So examples of compound events would be if you roll multiple dice or flip multiple coins, or if you're trying to find combinations of outfits consisting of shirts, pants, shoes, combinations of cards in a game of poker, spinning multiple spinners, rolling a number cube, and flipping a coin at the same time, or many more. Any two or more simple events that we put together form a compound event. So how do we find the probabilities of these types of things? Well, to do that, we're going to be using this ratio, which should look familiar by now. We've used it the last few lessons. So the probability of the event is still the number of favorable outcomes over the total possible outcomes ratio. The tricky part comes in when we're talking about the total possible outcomes. So the total possible outcomes in a compound event aren't always obvious. So we need to find a way to find the total possible outcomes. And to do that, it's all the possible combinations of the simple events. So we'll need to find an organized way to create what we call the sample space, or a list of all the possible outcomes. And to do that, some of the ways to do that are using a tree diagram, an organized list, or a table. So some way to organize the outcomes, because we're going to be listing all of the combinations of the ways these simple events can be combined. So a tree diagram is just a diagram that's used to show the total possible outcomes. Let's take a look at an example of a compound event. Here I have a coin and a spinner. And the spinner is divided into three equal sections, red, yellow, and blue. And then we have just a quarter that we're going to flip. So the coin is flipped and a spinner like the one shown is spun. What is the probability of it landing heads and blue like shown? So we want to know all the possible outcomes. So to do that, we need to create the sample space, list all the possible outcomes. And one way to do that is to use a tree diagram. And I've got an example of how to do that right here. So a tree diagram, basically, you're going to list all the possible outcomes of one of the events. So I listed the coin first. So there are two possible outcomes on the coin, heads and tails. And then from there, I branch off of each one of those outcomes, the possible outcomes for the spinner. And that's why it's called a tree diagram, because you're kind of creating branches. So if I get heads first, then I could possibly follow that with yellow on the spinner, blue on the spinner, or red on the spinner. And then you can see I listed those outcomes in the sample space on the right. So these are all the possible outcomes if I get heads first. I get heads yellow, heads blue, or heads red. And then secondly, I could have gotten tails on the coin, followed by yellow on the spinner, blue on the spinner, or red on the spinner. And then I list all of those outcomes here. So I could get tails yellow, tails blue, or tails red. And that's it. That's all the possible outcomes that I could have. And then this tree diagram helped me organize that and get that list. So once I have my sample space, then I can go ahead and calculate the probability using that ratio. So the probability of getting heads blue is the number of favorable outcomes over the total possible outcomes. So if I look in my sample space, I can see there are 6 possible outcomes to this compound event. So that's my denominator. And the favorable outcomes, well, the one I'm looking for is heads blue, and that is right here. And there is only one outcome that is heads blue. So my probability of this compound event is 1 out of 6, or 16 2/3% chance of getting heads followed by blue. So that's getting my sample space using a tree diagram. Here, students are assigned a temporary password for the first time they visit the computer lab. Temporary passwords consist of a letter, either A, B, or C, followed by a number, 1 or 2, followed by a letter, X, Y, or Z. How many different temporary passwords are there? And what is the probability of getting a password with a Z in it? So here I didn't make a tree diagram. I created what's called an organized list. I just listed all the possible ways that these events could be combined. So each digit in my password is a simple event, and I'm combining 3 of them together to get this compound event. So what I did is I started listing all the possible outcomes, or all the possible passwords by starting with just the letter A. So I listed all of the outcomes that start with the letter A. So A1X, A1Y, A1Z, A2X, A2Y, and A2Z. So I do it in an organized way, not just as they pop into my brain, because if you do that kind of randomly, it's hard to know when you've got all the possible outcomes. But if you do it in an organized way, then you can tell when you've got all your possible outcomes. Then I went ahead and listed all of the passcodes that start with B, B1X, B1Y, B1Z, B2X, B2Y, and B2Z. And then finally, all of the outcomes that start with the letter C, C1X, C1Y, C1Z, C2X, C2Y, and C2Z. So now I can see that those are all the possible temporary passcodes, and there are 18 possible outcomes. So what's the probability that I get a password with a Z in it? Well, there are 18 possible outcomes, and how many of those 18 have a Z in it? Well, since I listed all the passcodes in an organized way, I can see that all of these passcodes in the bottom row are the ones that contain Z's. So there are actually 6 passcodes that contain a Z. So 6 out of the 18. So my probability is 1/3, or a 33 1/3% chance of getting a passcode with a Z in it. Next, 2 dice are rolled. What is the probability of rolling greater than a 4 on either cube? So here I didn't use a tree diagram or an organized list. I made a table. So this is another way that we can create a sample space. And on the left side here, I have the first number cube that's rolled and all the possible outcomes, 1, 2, 3, 4, 5, 6. And then along the top, I have the second number cube and all of its possible outcomes, 1, 2, 3, 4, 5, 6. And then in the table, I just put the combinations of the two. So I could roll a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, so on and so forth. So this table shows all the possible outcomes of rolling 2 dice. And there are 36 outcomes possible. And so what is the probability of rolling greater than a 4 on either cube? So we're looking for the probability of greater than 4 on either cube. So now I need to look at these 36 outcomes and ask how many of these have a number greater than 4 on them. Well, it's going to be all of the outcomes in these 2 columns, because all of these have either a 5 or a 6 in them. And it's going to be all the outcomes in these bottom 2 rows as well, because number cube 1 has something greater than 4 in it. So all of these outcomes are going to have a dice that has something greater than 4 on it. So then I just count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 possible outcomes that have something greater than 4 on them out of the 36 possible outcomes. And this simplifies to 5/9, which is 55 5/9% chance. So there's a 55.5 repeating percent chance that I'm going to get something greater than a 4 on one of the number cubes. So really, this all depends on finding the total possible outcomes in a compound event. Are we always going to have to create the sample space? Are we always going to have to list out all the possible outcomes? Well, that doesn't seem reasonable when we start to get more and more compound events that have a lot of possible outcomes. So one thing we can use is something called the fundamental counting principle. And in words, it says if event M can occur in M ways and is followed by another event, N, that can occur in N ways, then the event M followed by N can occur in M times N ways. What? That sounds crazy. Well, basically, all you can do is just use multiplication. Multiply the total possible ways the simple events can occur together to get the total possible ways the compound event can occur. So the fundamental counting principle says that we can use multiplication to calculate the total possible outcomes of a compound event. So let me unpack that for you with the 3 compound events that we just looked at. So the first one was the coin and the spinner. Well, we can list all the possible outcomes to find the sample space, or we can use the fundamental counting principle. So how many possible outcomes are there of the coin flip? There are 2 possible outcomes of the coin flip. How many possible outcomes are there for the spinner? There were 3 possible outcomes for the spinner. So the fundamental counting principle says take 2 times 3 and that'll tell you the total possible outcomes of this compound event. There were 6 possible outcomes, and that's what we came up with our tree diagram. The next one was the passcode. The first digit of the password has 3 options, A, B, or C. The second digit had 2 possible outcomes, a 1 or a 2, and the third digit had 3 possible outcomes, an X, a Y, or a Z. The fundamental counting principle says if I take 3 times 2 times 3, that will tell me how many possible outcomes there are to this compound event, and there are 18 possible outcomes, and that's what we came up with our organized list as well. And then finally, with the 2 dice problem, how many possible outcomes are there when we roll 2 dice? Well, dice number 1 has 6 possible outcomes, and the second dice has 6 possible outcomes. So the fundamental counting principle says multiply them together to give us our 36 possible outcomes, and that's what we came up with the table. So the fundamental counting principle can save us a lot of time when we're trying to calculate the total possible outcomes of a compound event. So let's take a look at a couple examples of using the fundamental counting principle to find the total possible outcomes. Here, Lamar is going to spin each spinner once. What is the probability that he will spin red and the number 9? So the first thing we need to do is find the total possible outcomes. Well, on this first spinner, there are 5 possible outcomes: red, blue, orange, purple, or green. And on the numbered spinner, there are 10 possible outcomes, 1 through 10. So the fundamental counting principle says if I take 5 times 10, that will tell me how many outcomes there are, and there are 50 possible outcomes. That tells me my denominator in my probability. I know there are 50 possible outcomes. So what's the probability that I'm going to get red and a 9? Well, for that to happen, the spinner would have to land on red on this spinner and 9 on this spinner. There's only one way that can happen, is if the spinner's on red and if that spinner's on 9. So there's one of those outcomes that is red 9 out of the 50. So there is a 2% chance, or a 1 in 50 chance, that I'm going to get a red 9 out of this compound event. 3 number cubes are rolled. What is the probability of rolling 3 5s? So how many possible outcomes are there when we roll 3 dice? Well, the fundamental counting principle says multiply all the outcomes of the simple events together. So the first dice has 6 outcomes, the second has 6, and the third has 6. So 6 times 6 times 6 is 216 outcomes to this compound event. It's a good thing we didn't have to make a tree diagram or a table for that. That's a lot of outcomes. So this is where the fundamental counting principle really helps us out with some compound events. So I know there are 216 possible outcomes. How many of those outcomes are a 5, 5, 5? Well, there's only one way you can do that, is if there's a 5 that shows up on each of the dice. So if there's a 1 out of 216 chance that you're going to roll all 3 5s. Not a very good chance, because this is about a 0.46% chance that that's going to happen. So slightly less than 0.5% chance that you're going to roll all 3 5s on the dice. Okay, so that is finding the probability of a compound event. So our first objective is to find the total possible outcomes, and that's using either a tree diagram, an organized list, or a table, or using the fundamental counting principle. And then once we have the total possible outcomes, we're going to calculate that probability using the ratio we've been using the last few lessons: favorable outcomes over total possible outcomes.